Hey, it's Eamon with IP Exchange coming at you with the second video in our series on photonics with SuperLight Photonics. And this time I'm joined with Haider Zia, and we're going to be talking about the technology itself, the SuperLight Photonics Supercontinuum laser. So Haider, first of all, would you like to introduce yourself and what you do at SuperLight Photonics?
Yeah, for sure. So I'm the founder and CTO of SuperLight Photonics. And what I do is build on the IP and advance the technology, the fundamental technologies behind our products and behind the process that we exploit to have these wide bandwidth lasers.
Excellent. So the first question I'd like to ask you, Haider, is what is a supercontinuum laser and how does this differ from a typical monochromatic laser?
Very good question. So a supercontinuum laser is having hundreds of monochromatic lasers, each at a different wavelength, all at once, basically. So it's a coherent laser, but with a wide spectral bandwidth. And this is in opposition to the typical kind of traditional laser sources that we're all acquainted with, like laser pointers and so on, where you just have a singular frequency that's outputted, but it has all the advantages of those laser sources. So besides the monochromatic frequency that it outputs, it also outputs a very, very narrow beam that's collimated over wide distances, and the beam is not fluctuating in space and in time. It's very constant and very stable. So a wide bandwidth laser has all of that, but more colors.
Excellent. So you mentioned the supercontinuum laser having all the benefits of a monochromatic laser, but across a broad spectrum of bands. How does this compare to, say, a broadband light source? And what applications would you use a supercontinuum laser for that you wouldn't necessarily use a broadband light source for?
Yeah, that's also a very good question. So a broadband light source, for example, a halogen lamp or an LED source, they indeed have a wide variety of colors that they output, but they don't have what we call the coherence of a laser. So when they emit light, they emit it always in this wide three-dimensional angle called a large solid angle. And the radiation that's emitted is very fluctuating and noisy. So it lacks a lot of properties that we need, for example, in high-end applications where we need very precise measurements of objects at very precise locations. So there you would need really a very well collimated beam or a very well focused beam with a multitude of colors to carry out information, to gather the information from the object.
Nice. Tell me a bit more about SuperLight Photonics supercontinuum laser. What makes it so disruptive on the market compared to what's out there today?
Yeah. So basically, the IP is based on my idea that I developed in my research at the University of Twente in my postdoctoral phase. And the idea is really to bring supercontinuum lasers into the photonics integrated platform, and to really downscale these lasers such that they could eventually fit on chip. And the way I did that was to make the generation process more efficient on chip. So essentially, instead of having these very large, bulky lasers that's needed to drive the process, we now have it can be driven with very, very small lasers that are low power relatively to what was required before. And yeah, we could get factors of thousands more in efficiency actually with this IP that I came up with.
So there's going to be a lot of laser physicists and laser technicians out there who know what a typical laser setup looks like. So what does the SuperLight Photonics supercontinuum laser look like when you compare it to a typical monochromatic laser?
So our products start with our major value add, which is a photonic integrated circuit that contains our pattern alternating dispersion technology. So basically, we have right now one of the world's smallest seed lasers, a fiber laser that's pulsed. It's pulsed on the hundreds of femtosecond scale. This laser is then fed into a lensed fiber, which goes into our chip and produces this supercontinuum generation. And actually, we can produce wide spectra of 400 nanometers or above already at 0.8 milliwatts of power.
Okay.
And that, compared to our competition, is like compare 0.8 milliwatts to 3 to 6 watts of power, and you see the efficiency of going in this technology and in the PIC, in the integrated photonics space with supercontinuum lasers.
Nice.
In conventional supercontinuum lasers, you see the waveguide with a pulse, but then the pulse broadens in time and it loses its power. It specifically loses its power to generate spectra. But our technology actually shapes the pulse such that it continuously generates spectra in the waveguide and extends the generation length possible. So you can imagine like a pulse being squeezed in our waveguide in all sorts of ways to maximize the bandwidth generation, but at the same time we have puffs of blue and green and yellow light coming off of this pulse that are also highly useful for visible light applications. Then we interface this with the smallest fiber laser that we could find in industry, and the two come together to make this functional product.
So, thank you so much, Haider, for taking us through that. We've also got a third interview with SuperLight Photonics coming soon, which will be about applications, so you can look forward to that. But if you want to learn more about the supercontinuum laser from SuperLight Photonics, check out the write-up I did on the IP Exchange website, where you can also apply to evaluate the technology for use in a commercial project. Thank you again, Haider, for joining us, and I look forward to talking to your colleague for part 3.
Thank you for having me on board. I hope it's as interesting to you guys as it is to us.